Good afternoon. Today we'll be presenting our process, our attempts to recreate the process of field-assisted sintering of advanced random materials. This is Alejandro, Vera, Nikhil, Mohip. My name is Seth. My advisor was Dr. Yushin. Here's a presentation outline of our presentation. We'll be given the problem statement, literature survey, related standards related to our project, the challenges that face the team, our global design components, initial die design, as well as iterations of our actual die design, engineering, design, and analysis, our current design, prototype construction, testing, and evaluation of what we did in the Sabri lab downstairs, design considerations that we took into account, integrated global design aspects, commercialization of our process, future design, and conclusion. For this project, we wanted to recreate the process of flat sintering. It's a new field, so we wanted to investigate it and then also recreate the process of it. The motivation behind this is to investigate the benefits of flat sintering as opposed to conventional sintering. Our goal was to successfully recreate the process and compare the benefits of it compared to conventional sintering. Sintering is a manufacturing process where a solid mass is created through the application of heat and or pressure. This can be applied to ceramic powder, metals, as well as plastics. However, there are different types of sintering. Our team focused on field-assisted sintering. During the literature survey, we found that applying a DC current to a ceramic powder while it's in a furnace will allow for densification within 5 seconds. That's why they call it flat sintering. In conventional sintering, it takes upwards of 24 hours. For our project, we focused on the International Organization for Standardization. They had a number of standards related to fine ceramics. One challenge that we faced as a team was to successfully recreate the process in the Sabri lab downstairs. A lot of materials require temperatures of 1500 degrees flat sintering. We have furnaces that can reach that, but we want to do it at temperatures lower than that. We also wanted to densify material up to 90%. We were told by a number of the staff and TAs in the materials engineering department that it's extremely hard to do. So we wanted to reach 90% and then reach upwards of that. We also wanted to record temperatures in real time because, as you'll see later, the furnace is closed off. So it will be hard for us to record temperatures in real time. For this project, the power supply that we ordered was from Germany, so we had to convert euros to US dollars. We also wanted to translate our projects into German because that's where the research has been done, where they successfully recreated the process. We also wanted to find ways to implement our process in industry. If we are successful, then this will help out a lot of industries that work with ceramic materials. Here is our initial die design. During the literature survey, we found that the die bone shape allows for even current distribution. However, when we machined it, we found that the tolerances between the extrusions on the side and the cutout in the middle weren't viable for us to use. So we used the initial conventional die that was actually supported, that was provided by the Sabri lab downstairs. For this, we did have to take into account safety when we chose materials. Each stabilizer cone that we found during the literature survey was a material that's easy to work with. This was also provided down in the Sabri lab. However, silicone carbide was found to be extremely difficult to flat sinter without using magnets. So we wanted to use each stabilizer as a stepping stone to silicone carbide. Each stabilizer cone, as I said, is an easy powder to work with, so we wanted to experiment with this to get familiar with the process, to get familiar with pressing the powder in the die, and then to get used to using this in the lab. This is a formula that Alejandro will explain.
Okay, so it is proposed on the literature survey that flat sintering occurs because of a spike in temperature once electric current passes through the sample. There's a formula that is used to predict the temperature that the sample will reach, and that's called the Joule heating formula. Here in the equation, T0 is our surface temperature, which will be the temperature at which the furnace is heated up to, and then once the electric current passes, which will be the power value, then you can calculate based on the area, surface area of the sample and the emissivity, and you can find the final temperature of the sample that you reach once it successfully sinters. Here, before we started our experiment, we wanted to predict the temperature that it would reach. So we did some modeling, we did some trials with using the power supply capacity that we purchased, and using the sample dimensions and the material properties. We came up with this model for different trials. Of course, the temperature increases as the power increased, and using the data from the model, we can see that with respect to time, as the temperature increases, and once we pass the electric current, there should be a spike in temperature, a very high spike in temperature, which is what ultimately would sinter the material. This is a current design that we have in the laboratory. We have a horizontal furnace, we have a glass tube, and we have the sample placed inside. And then we have platinum wires to the sample, which will pass the electric current to the sample. This is a solid modeling of our current design in the laboratory. As you can see, this is a sample here. This is an aluminum oxide plate that is used to hold the sample on the glass tube so that it doesn't burn the tube, and you can hold the sample in place so it doesn't move. And now Nikhil is going to talk about the prototype construction.
So for our prototype, we had some basic components. We used the power supply that we purchased. We used an ATS furnace, and we used a die, and we used platinum wires to connect everything. So first off, we had Sorensen X100 power supply. It was a 1500 watt power supply. So we had 100 volts at 15 amps that we could go up to. This is us connecting the power supply to the AC portion of the power supply, so we can just plug it into the wall and use it. Then we use the ATS temperature control system tube furnace. This is the furnace open, and that's when it's closed with the tube inside of it. This is the glass furnace tube that the sample was placed inside of. So for the procedure, we had to prepare the ceramic pallet, then set up the power supply, set up the furnace, apply the constant heat, and then run the current once it got to the temperature. So this is us weighing out the ceramic powder in the lab, and then pressing it inside of just a pneumatic press. We took the sample and placed it on top of the aluminum oxide that was used as a shelving. Put that inside of the tube furnace and just slid it into the middle of it. Then was one of the harder parts was getting the platinum wire to connect to one end of the sample. So we fed it in from one open end, and then secured it with the insulating block so the wire would stay still. And then we would do that on the other side with the other wire, the electrode. So we got it touching, and then we'd secure it on the other side. Then we close the furnace, program it to heat up, and wait for it to reach our initial temperature we needed. Once it reached about 905 degrees Celsius, we introduced our current to the sample and hope for the best. Then we allow the furnace to cool, which takes about 4 hours to cool down, and then we were able to test our sample.
So some of the considerations to work in the lab is safety considerations. We had to wear safety goggles, safety masks, safety gloves, lab coat, and we had to be very cautious with handling the ceramics because a lot of ceramics can be carcinogenic, so we had to be very careful there. As well as reading the manuals for the power supply, reading the manuals for the furnace, having to study all those so that we could use them correctly, as well as taking training classes from the American department. Another consideration was the dye tolerance, as mentioned before. This was our design for the to understand this process, we use the dye. We place the ceramic powder inside, and then we use a pressing, and we apply a force pressing the powder using the dye, and then that would make it solid but still brittle, and then we put that sample inside the furnace. So this was the dye that we designed, but as you can see, some of the tolerance for machining here it was the gaps were too wide, therefore it was hard to remove the sample from it. This is because our budget was $400, this cost $400, and to design dies that can hold a lot of tolerance could go up to $1,000. Some of the design aspects here, well, the purpose of this experiment, if it was to be implemented in the industry, is to speed up the process of manufacturing ceramics. A lot of companies that deal with ceramics, they use conventional sintering, which can take more than 24 hours to do. By using flash sintering, you could sinter ceramics in less than 5 seconds, and you can save a lot of money in electricity and therefore make the products more available to the customers. Like I said before, implementing flash sintering into the manufacturing industries would be the ultimate goal of this process. So here is our future developments, which is what like he said, the biggest challenge was to put those platinum wires and make them connect to the sample. There was a lot of human error there because once you close the furnace, you cannot see what's going on with the sample anymore. So we came up with this solution to use the aluminum oxide and have a piece of a tube, a ceramic tube with holes in there to connect, to pass the platinum wires through them and attach them to the dog or the sample that we're going to use. Then use a ceramic binder to bind it and using some ultraviolet light, heat it up so that it's for sure connected, therefore reducing the human error. Also, using this prototype, we could use a thermocouple, pass it through one of the holes as well, and do the same thing, connect to the sample so we can read the sample's temperature in real life, in real time. This is a solid modeling of our final, of the proposed development and the future work for our design to be more efficient. We used that design to run one trial because of the amount of time that it takes to run each experiment. It's about 4 hours of constant heating, an hour of soaking it in that constant temperature of the furnace, and then cooling it down in 4 hours. We were only able to do one trial using our future development prototype, and after we took out the sample, we saw some discoloration, which means that something actually did happen to the sample. We also observed a sparking light coming from the furnace, which is that flash that comes off shows that the current is passed through the sample. And we also noticed that the platinum wires melted. Platinum melts at 1700 degrees, and platinum melted, which means that the temperature reached well above that temperature. So some future things that we would like to do before the end of the year is to continue to try out this prototype and to test the ceramic samples that we think successfully sintering.
So in the future, we hope to laser cut dog bone shaped die in the lab. We already have that machine, and so we're going to use a green pellet and laser cut that shape out so it's more ideal. And as you saw, using a different apparatus to hold the wires so that the sample can sit down on top of it more accurately. And we could also use the thermocouple to measure it in real time at the same time.
Thank you for your time. We appreciate it. Are there any questions?
Yeah, actually, so it's funny because my doctoral dissertation work was on sintering ceramics. So that wasn't the main thing, it was a byproduct, and I had to sinter it, and it was old-fashioned school, a graphite furnace going to 2900 degrees C, and you had to ramp it up and stop for a while, and ramp it up and stop for a while. So it came out really nice compared to that sample, but the question is, what is you supposed to scale on this? I mean, how do you control the current going through that sample? If you get more, if it doesn't go all the way through evenly, don't you going to get uneven sintering?
Yeah, so the reason that we chose the dog bone shaped die, that dog bone shape is supposed to allow the current to travel more evenly throughout the entire sample. And our power supply, we could put exactly how much voltage and what wattage we need. And so the hope was using that die to get it to sinter successfully, like go evenly flow through the sample.
Right here on the top left with the numbers on the right, there's a knob to control the amount of amps output as
Right.
well as voltage. A lot of dollars.
So how many amps were you using?
We did different trials. We did all the trials. We used different combinations of features sterilized cornea. We tried plain sterilized cornea. We tried sterilized cornea.
On our-
mixed with binder ceramics.
On our last trial, we used 10 amps at 100 volts to see if we could get it to work at all, and it did. We got a lot of activity out of it, and melted the ceramics, melted platinum. So we know now we got to go way down on it.
Or change materials?
Yeah, well, we're gonna get the Yttria stabilizer zirconia to center first, and then start moving towards.
So what's the final use of that? What's it for?
What we did is just to experiment with flash sintering to see if it's possible. If we can, we'd like to move on to see maybe pottery or other applications.
We have a grad student right now that's going to use this same kind of procedure in her work. So we're trying to get this whole thing, this process working so that they can use that in future years over here.
You didn't get to do any SEM work to check first surface morphology, see porosity, how everything changes?
So yeah, we have
to
a
coast?
sample right now, and it's being tested. We're doing the XRD testing and SEM sampling testing on it right now to see exactly how much it's sintered. So
How many pounds of pressure do you put on that, on the die?
1 ton of force. So I mean, it's not a lot of
It's not a
pressure.
lot.
No.
But doing
That's-
25,000 pounds.
That's what we were instructed on, so we're supposed to press that pallet.
The question I want to throw at you is, how would you redesign the experiment to ensure that you had a uniform spark distribution across the ceramic?
We did find that a vertical tube, you get to hang the sample along the wires down. As you see in this, that's the aerial view, but other experiments have been done with this where it's vertical. Ours is horizontal, so we not assume, but we would like to test it out where we hang it and we have electrodes on each side. So that will allow even current distribution.
I mean, with the lab you're working in, you could put down a conductive path on that ceramic and then design it to be a fuse.
Yeah, I mean, that's
and
basically what
control those cavities.
That's what our design is.
So
The new design is basically, so we have platinum wire running through a ceramic tube that comes down and is glued with ceramic bond onto the aluminum oxide plating. And then just the end of the wire is sticking up on both sides, so positive and negative, real close together so that the.
But I mean, that gap is really critical.
Yeah, so yeah, there's a gap, we have a gap there, it's already glued and everything, we have one built. And that way we can place a sample right on top of it. And then using silver conductive paste, hopefully get it to attach even more secure onto those electrodes without falling off in any kind of way, keeping the gap secured.
But I mean, I would think you'd want to have a uniform spark formation
Yeah.
across the whole structure, because what you're going to get with a single spark is you're going to get a single dense section radiating out to none.
Yeah. So, I mean, we're still working on designs, and I really hope to get this working before we leave this school, but that's the goal is to get this working for the future generations of students.
So would it be possible to collaborate and maybe do
Oh,
a
you could call me anytime, but I'm old school with this stuff. I mean, this stuff was just like normal way of doing it, which is just ramp it up and go up to 2600 degrees C and a graphite furnace and vacuum. And that's how I did them. But that was my main research. My research was nuclear decontamination. And the product was aluminum ceramic when you reacted aluminum metal with nitrate waste. So I was just a byproduct, but you know, have to help any way I can.
Thank you for your time.
Thank you.